So, we have done all the consequences of Lorentz transformation. There is a very nice geometrical representation of all these transformation equations. With each event you can assign some kind of a vector quantity, and space and time, space coordinates and time coordinates may be treated as components of that vector. You have seen in this transformation that space and time gets mixed up. T prime is equal to T minus x v by c square divided by square root 1 minus v square by c square. Then x prime is x minus v t divided by square root 1 minus v square by c square. Y prime is y, z prime is z. We have taken motion along the x axis only, therefore, these coordinates do not change. But here the time and this x, they get mixed up to get that t prime. You have t as well as you have x. Similarly, to get this x prime, you have this x as well as this t. So, as long as you are in one frame, very nice, space is separate, time is separate. But when you are changing from one frame to other frame, there also space and time are different, but then that space coordinates, they are a combination of space and time coordinates in this frame. So, just like if you have a vector, if you just put one let us say, suppose you have an axis system, this is x axis, this is y axis, and you have a vector. So, as long as you are in this frame, you are using this coordinate axis, you have a component a x, a definite component a x and a definite component a y. But if you rotate these axes and go to some other axis, let us say this is the new axis, this is x prime and then this is y prime. So, we have rotated our axis system about the z axis, common z axis, and say this angle is theta. Then you have the same vector, but the components are now different. Now, components are different, this is x axis. So, this becomes the x component and this becomes the y component. And if you write this component a x in terms of a x prime and a y prime, you see that the two x and y components will get mixed up. So, let me draw this diagram slightly magnified form. So, let us say I have these are the new axes, and then I have a vector a, this is some vector, or let us say position vector, let us say this is a position vector. So, the coordinates are x and y. So, if I drop a perpendicular here, this is x and this whole thing is y, and if I drop a perpendicular here, then the coordinates are x prime, y prime. So, this whole thing is x prime and this whole thing is y prime, this is y prime and this is x prime. You can drop a perpendicular from here, you can drop a perpendicular from here. If this angle is theta, this angle will be theta, and then you can write x, try to write x. What is x? This is x. This x is equal to, this x is equal to this length, and this length you can write x prime cos theta. So, this is x prime cos theta and minus this length is this is y prime sin theta. So, this is y prime and sin theta. Similarly, if you want to write y, so what is y? What is y? This is y, this is y, this is our x axis, this is x prime axis, this is y axis, this is y prime axis. So, this is y. This can be written as this length and plus this length, and this length is same as this length, and that is x prime times sine theta. So, this is x prime times sine theta, and plus x prime times sine theta is this length, which is this length, and plus this, and this one is y prime times cos theta. So, plus y prime times cos theta. If you want to write the reverse x prime, you only have to replace theta by minus theta. So, x prime will be x, and cos theta and cos of minus theta are same. So, it will remain cos theta. Sin theta will become minus sin theta. So, it is plus y and then sin theta. And this y prime will be, here the sign will change. So, minus x prime minus x sin theta and plus y cos theta. So, these are the transformation equations, and you see that when you change the frame from this, let us call it s frame, and let us call it s prime frame just for this lecture. So, when you are going from s frame to s prime frame, what do you see? You see that the new x prime is a mixture of old x and old y, and similarly new y prime is a mixture of old x and old y. Compare with the Lorentz transformation when you are going from s to s prime. New time coordinate, this new time coordinate is a mixture of the old space and time coordinates, and similarly the new space coordinate is a mixture of old space and time coordinates. So, it is as if you have a single space time entity, space time vector, and then when you have fixed your frame, inertial frame S, the space and time coordinates are just component of that space time vector, and as long as you are in that frame, fine, good, very good. So, space is separate, time is separate, x component separate, y component separate. Any force in x component does not affect motion in y component, and so on. So, they are separate. But when you are changing from s to s prime, space time vector remains the same, the components change, and therefore, the space coordinates and the time coordinates change. So, that is a kind of vector associated with our events and geometrical representation. So, let us try to explore that. Now, this if you write, let us write z prime equal to z also. So, this whole thing can be written as, this thing can be written as in a matrix form. You have x prime, y prime, z prime, and then you write a square matrix here, and again the column matrix here, x, y, z. So, from x, y, z you are going to x prime, y prime, z prime, and then you can just see that if you write cos theta here and sin theta here and 0 here, then minus sin theta here, then cos theta here and 0 here and 0, 0, 1. So, if you multiply the matrices, I am sure you know how to multiply matrices. This is 3 into 3 matrix, and this is your column matrix. So, when you multiply this, the first you will get a column matrix, that is the column matrix, and the first term here, so that gets multiplied x cos theta. So, that is x cos theta plus second term here, so y sin theta, so plus y sin theta, and then third term here, that is 0, so nothing. Similarly, y prime you can write, it will be minus sin theta into x, so minus sin theta into x, plus cos theta into y, so plus cos theta into y, and then 0, this 0 multiplied by this z. So, that is it. Then come here, z prime should be equal to this term into this term, that is 0, plus this term into this term, that is 0, plus this term into this term, that is z. So, z prime is equal to z. In fact, many times this transformation equation itself is taken as the definition of a vector. Any set of 3 quantities which have some definite rules to be constructed, and when you rotate the frame, and you find that the new quantities according to those rules are these, and they are related by this relation, that makes a vector. That is the definition of vector. Now, let me work on the Lorentz transformation, this one, and let me multiply the first one by C. So, it is Ct prime is equal to Ct and minus x v by C, and then this whole thing divided by square root 1 minus v square by C square, and let me write it as Ct and minus x into beta and times gamma. So, I put gamma here, I put gamma here. You know, gamma is 1 by square root 1 minus v square by C square. Beta is v by C. I am using the symbols. Gamma is 1 by square root 1 minus v square by C square. Ct prime is this. Then x prime. X prime is equal to x gamma and minus beta into Ct. This is v by C, so this becomes minus Vt, and then gamma. Y prime is equal to y and z prime is equal to z. So, you can write Ct prime, x prime, y prime, z prime equal to, let me write a square matrix here, and this side it is Ct, this side it is Ct, and then x and y and then z. What I should fill here? Ct prime is equal to Ct into gamma. So, Ct into gamma, I should put gamma here, then minus x into beta gamma. So, x is here, so minus beta gamma and then 0 0. Just check. If I do this matrix multiplication, first row and first column, that gives me this 1 1 component. So, gamma times Ct, it is here, minus beta gamma times x, it is here, then 0 times y is 0, 0 times z is 0. So, that first transformation equation comes from here. Second, x prime, second row and this column. So, Ct minus beta gamma. So, this is minus beta gamma, and then x is multiplied by gamma. So, this x is multiplied by gamma and then nothing. So, 0 0. What is y prime? Y prime is y. So, y prime you can write 0 0 1 0. Check. This row and this column multiplied will give me this 0 into Ct plus 0 into x plus 1 into y, and then 1 into y is here and then 0 into z. So, I get this one, and similarly z prime is equal to z. For that it will be 0 0 0 and 1. So, 0 into Ct plus 0 into x plus 0 into y and plus 1 into z. So, it looks like I am doing this kind of a transformation, right. I have 4 components now. Here it was, there were 3 components, and then there was a matrix 3 by 3 matrix, and that theta decided that new frame from the old frame. So, here also I have column vector 4 components, column vector 4 components, then there is a transformation matrix that takes me from this to this. So, it is a kind of transformation, and from S to S prime the key factor is that V. So, that is in this beta gamma. Here the key factor was theta. So, that theta was coming here. So, here the key factor is that V. So, that V is coming here. So, that is the kind of idea try to conceive. It is an abstract idea. It is a mathematical representations only. So, try to conceive, you have a single vector for an event, a single vector, we call it space time vector, okay, you can call it that way. and then space coordinates and time coordinates, they are components of this in the when you are in S frame. When you are going to S prime frame, which is moving with a velocity v with respect to S in positive x direction, as we had defined, t is 0, t prime is 0 when origins cross and all that, you are changing the frame. And when you are changing the frame, the components do get changed, and the new components are obtained from the old components. They get mixed up to give you these ones, just like here, just like here, they get mixed up to give you the new coordinates, and then this is a transformation equation. So, this one, this matrix is the transformation equation. Now, we can go little further. First, let me tell you some notations which are commonly used. One is in this all this mathematics, what we do is we use not like x, y, z, but we give symbols x1, x2, x3. So, x is the vector, and then the first component will be x1, second component will be x2, third component will be x3. So, let me make some space and let me describe these symbols. So, let me say we name our vector as x. This is x, position vector, and the components which we usually call x, y, z components are x1, x2, x3. So, this is x component, this is y component, and this is z component. So, if I name it like this, then let me say what is dot product of two vectors. Suppose I have two vectors, one vector is A, another vector is B. So, what is the dot product? We call it A dot B, and normally we say it is Ax Bx plus Ay By and plus Az Bz, where Ax, Ay, Az are components of A and Bx, By, Bz are components of B. In our symbol we will not use x, y, z, we will use 1, 2, 3. So, in that case this is A1 B1 plus A2 B2 plus A3 B3. This is the scalar product or dot product. You can write this as a summation over I Ai Bi. So, that is why I am using 1, 2, 3, so that I can write it in this particular form. Summation over I, that means I will take 3 values 1, 2 and 3, you will get 3 terms. When I is 1, it is A1 B1, when I is 2, it is A2 B2, when I is 3, it is A3 B3, and sum of all these 3. So, that is this scalar product. There is another convention, and that convention is that if you do not write this sigma I and only write Ai Bi, it is understood that you have a sigma I here. If a particular index is repeated, Ai Bi, I is repeated, so that implies that there is a summation sign here. That is also a convention, and we will be using perhaps this convention. Now, if you take dot product of a vector with itself, then it will be summation over I Ai Ai. So, it is summation over I Ai Ai, and that is A1 square plus A2 square and plus A3 square. And if you take a square root of this, if you take square root of this, what you get is magnitude of A. And that is invariant when you rotate the axis. So, when you rotate the axis, this magnitude does not change, A1 changes, A2 changes, A3 changes, components change, but this thing will not change, magnitude will not change, this dot product will not change, it will remain there. And if you have two vectors A and B, if you have two vectors A vector and B vector, and you construct this quantity A1 minus A2, A1 minus B1 square plus A2 minus B2 square and plus A3 minus B3 square. Think of two position vectors, one is here and one is here. So, here the this is say y vector. So, here the coordinates are x1, x2, x3, and here the coordinates are y1, y2, y3. What is this x1 minus y1 whole square? A1 minus b1. So, what is this x1 minus x2 whole square plus x2 minus y2 whole square plus x3 minus y3 whole square? The x component difference square, y component difference square, and z component difference square. That is the distance square between these two. Okay? So, this distance is square. So, this distance, if you write d, then this d is square root of x1 minus y1 square, x2 minus y2, difference of y coordinates square, and plus difference of z coordinate square. This whole thing is your distance that is also invariant under this rotation. You rotate the axis, this distance is not going to change. So, magnitude of this is not going to change, magnitude of this is not going to change, the distance is not going to change. These are invariant quantities under this rotation. Can we do something like this here also? So, let us start with defining magnitude. So, now you have four components. So, let me once again define them by an index 1, 2, 3, 4. So, I have some event which is given by, let us say, this x, y, z and t, and these are the four coordinates. So, Ct, let me rename Ct will be written as x, let us say 0 here. There is a reason, okay, let me start with this, we will switch there. Call it 0 component, the time component. This time component, let us call it 0 component. Instead of 1, 2, 3, 4, we will go 0, 1, 2, 3. So, this is 0 and 1, 2, 3. So, Ct if I call x naught, then x I call x1, y I call y1, and z I call z1. So, that will be x2, this will be x2 and this will be x3. So, that will be our symbols. Event, remember I have an event in mind, there is an event in S frame, its location is x, y, z, x, y, z, its timing is t in S frame, and corresponding to that event and these space coordinates and this time coordinate, we are defining these symbols. The first component which I write x naught is this, the second component, that means the x coordinate in our usual terminology, that is here, and x1, then y component of that event, location, y coordinate of the location of that event will be named as x2 and z coordinate of that event will be named as x3. So, this is now, if you write it again, this will be x naught prime, and this will be x1 prime, and this will be x2 prime, and this will be x3 prime. This is how we will write. this is that rotation, that transformation matrix, and then here you have x naught, x1, x2 and x3. If I try to write the magnitude of this, normally I would have gone for x naught square plus x1 square plus x2 square and plus x3 square. Normally, if I want magnitude of this, how will you write magnitude of this? These are the coordinates. So you will say that okay, this particular magnitude, let us say just x is equal to this coordinate square plus this coordinate square plus this coordinate square. So in that same spirit, if I square all the 4 components and add in our usual symbol, what I will get? I will get ct square plus x square plus y square and plus z square. This will be the magnitude square. But you know that this quantity is not invariant when you do Lorentz transformation. When you go from S frame to S prime frame, now this S prime is usual relativistic. So in S frame these are the coordinates, in S prime frame these are the coordinates for that particular event. And this quantity is not invariant, this is not invariant. But if you put a minus sign here and a minus sign here, it becomes invariant. Okay? You could just apply Lorentz transformation and see that this quantity does not change. So can we redefine our scalar product little bit? And that is being done. That people do, and what they say that when you are having say 2 vectors A and B, 2 events, okay, there you have 2 events A and B, and correspondingly you have first event you have let us say A naught, A1, A2, A3, these are the components. So the first event occurred at these x, y, z coordinates and at a time t, c times that time is this A naught. Then you have another, so this is one vector, this is one vector, and then you have another vector say B naught, B1, B2, B3. This is another event and correspondingly another set of coordinates. And if you have to define A dot B, what you should do is first component when you are writing A naught, B naught, put a minus sign here. This component A naught, B naught, put a minus sign here, plus this is okay, A1, B1, plus A2, B2, plus A3, B3. If you define this way the dot product and take dot product of a particular vector with itself, then you will have this A dot A, which is minus A naught plus A1 A1 plus A2 A2 plus A3 A3, and that is minus, this is CT, this is CT, so minus C square T square and plus A1 square, that will be the x coordinate square. Okay, let me write that way, x coordinate square, this is y y, so this will be y square and that is z square, and this quantity will not change. So define magnitude, define dot product by this equation, and correspondingly that definition remains the same, take dot product with itself, that gives magnitude square, magnitude remains invariant. And then if you have 2 vectors, if you have 2 vectors A and B, 2 events A and B, the corresponding vectors are A and B, these are 2 different events, and then you construct this quantity A naught minus B naught square plus A1 minus B1 square plus A2 minus B2 square plus A3 minus B3 square. Just like this, just like this. If you construct this quantity, this will be essentially C square T1 minus T2 square plus x1 and minus x2. Now this 1, 2 are our usual symbols. 1 and 2 is for two different events, event 1 and event 2. So x1 minus x2 square, then you have y1 minus y2 square and z1 minus z2 square. So this quantity will be in our usual, so far we have used the symbols x, y, z, t. In those symbols this will be the thing, event 1 and event 2. But you know that this is not invariant. You have to put a minus sign here. So put a minus sign here. This is invariant. It's like the distance between these 2 points. It's like that. And we have to put this minus sign all the time, so that minus is here, and this quantity will be invariant, just like this distance is invariant. Now this quantity is called interval between the 2 events, not the time interval. Remember, not the time interval. Okay. So this quantity is called interval, you can write it as I, and this is again a Lorentz invariant. This does not change, just like this distance does not change. So these are the analogies from our geometrical vector space. We have taken the analogy and we are constructing a 4-dimensional vector space in which the components are Ct, 0th component we call it, then x coordinate first component, y coordinate second component, z coordinate third component, and then we construct our algebra, vector algebra. We define magnitude of that vector, we define dot product between these 2 vectors, then we define interval between these 2 vectors. So that vector algebra can be constructed, it is very, very useful. Now such vectors, when we define such vectors which are transformed when you go to S prime according to this Lorentz transformation, are called 4 vectors. We call them 4 vectors, we write it this way. 4 vectors, it will have 4 components. If you just define an event, and for that event you have time coordinate, x, y, z coordinate, and then you construct this these 4 components, Ct, x component, y component, z component, this particular vector which gives you one event, one particular event in one particular frame. These are the coordinates, this is the time, this is the position. If you change the frame, then of course the components change, the time changes and x, y, z coordinates may change, right. So that is known as, that particular vector is known as position 4 vector. This is position 4 vector. It has time also, but it is usually called as position 4 vector. So position 4 vector is the time coordinate of an event multiplied by c, and then x, y, z components for the spatial location of that event. So that is known as position 4 vector. And any set of 4 quantities, any physical quantities which can be represented by 4 components, and if those 4 components transform on going from S frame to S prime frame according to this equation, will also be called a 4 vector. Here you have position vector, but you also have many other vectors, linear momentum vector, you have angular momentum vector, you have force vector, you have velocity vector. All the vectors obey the transformation equation when you rotate the frame, the same transformation equation, same matrix. So anything which obeys that transformation matrix will be a vector. Similarly here, Ct, x, y, z, they obey this transformation equation, this Lorentz transformation equation. Any other physical quantity which can be represented by 4 components, not necessarily time component and position component, but 4 components, and if those components change when you go from S to S prime in this particular fashion, they qualify for being called a 4 vector, and we will come across many other 4 vectors also apart from this position 4 vector.